Alright, so today is 14, 19. Alright, so this is Newton's second law of motion. So yesterday we did one on Newton's first law of motion, which is object in motion wants to stay in motion, and an object at rest wants to stay at rest. And that's pretty much the basis of it. Now, Newton's second law of motion is pretty much summarized right here. F equals m times a. So force equals mass times acceleration. So we're going to look at this little box right up here. The magnitude, kind of like the measure, the amount of force. So let's say like a magnitude of a 6.7 for earthquake. So it's just telling you kind of how much force is in it. So the magnitude of force is equal to mass multiplied by acceleration. Okay. And most of the time this is going to be in meters. Oops, what time is it? 2:45 meters per second squared. And this is going to be in kilograms. Okay, because we use what the rest of the world uses, which is meters and kilograms, not pounds and feet or inches. So, what did I use yesterday? Oh, we got a little kitty cat here. Well, I think we're going to need a couple of them. So we'll have a kitty cat and a goat. Oh, they're friends. So looking over here, looking at this little circle right over here, I'll zoom in a little bit more. Blank is produced when a blank acts on a blank. This is going to be acceleration. Excuse me, Mr. Kitty Cat. Oh man, get your paws out of here. There you go. This little butt. Acceleration is produced when a force acts on a mass. An object can accelerate with a large push, or anything similar to that, I suppose. So now we have force, we have mass, we have acceleration. So we're going to be working on those next. So let's put the dog over here. Okay. Force is the blank acting on the object measured in blank. So this is pretty much the I'll use the pink, it's kind of small. The net force acting, that's an E by the way, net force acting on the object measured in newtons. So force will always be in newtons. So if you're doing some of the problems and it gives you something in N, or if you're solving for force, your answer should always have an N at the end of a capital N. So it's kind of hard to see, it almost looks like an H. Capital N. Okay, so that is going to be force. All right, Mr. Raccoon. Remember, never pet raccoons. They might have rabies. But I think they could be kind of cool pets, except for the whole rabies thing. And the fact that they like to chew and they have claws and everything else. Oh, I forgot to put this on here. Bad, bad. This, to solve for it, F equals M times A. Okay, so F ma. Okay. Mass. So mass is a little bit different than weight. Mass is doesn't change. Weight is all dependent upon by gravity. So if you went to the moon, or if you went to Uranus, your mass would not change, but your weight would, because the gravity is different. So the mass of an object is measured in kilograms. Okay. And to solve for this, it would be mass equals force divided by, goodness gracious, so annoying. Mass equals force divided by acceleration. Okay. Do we have any other like domesticated animals? Well, I put a raccoon on there, so I guess that's not domesticated. We'll put a duck. Or maybe it's a goose. I think it's a goose. All right, so acceleration. The acceleration of an object is measured in meters per second per second. So you will have to kind of measure it in meters per second per second. That's why it's squared. So instead of writing per meters per second, you are simply writing meters per second squared. So the acceleration is in meters per second squared. So 50 meters per second squared instead of like miles an hour. And to solve for acceleration, it would be A equals F divided by M, so force divided by mass. Okay. So unless otherwise stated, your acceleration, don't ever leave your numbers naked, should have a meters per second squared, just like your forces should always be newtons. And your, that's my train of thought there, so I'm trying to pick out a cool animal for a little chicken, I guess, or a hen. And your mass is always going to be in kilograms unless otherwise stated. Okay. So looking down here, we have a couple of graphs. I know you guys love, love, love graphs. I might as well get used to them. You're going to see a lot of them in your academic careers. So this is, we're going to put force down here. And it is abbreviated. This is a capital N. It's kind of a cursive N, so just, yeah. And if we know that this is in meters per second squared, what do we measure with that? We measure acceleration. Okay. So acceleration is going to go on the y-axis. Remember, y to the sky, x goes across. Here's your x, here's your y. So when mass is constant, okay, this is what the graph is going to look like. Okay, just a constant line. So when mass is constant, as acceleration increases, so does force. Okay, so it's just kind of a relationship graph more so than anything. So you don't need to do anything else with this. You're just looking at it. Okay, ta-da, cool. All right, I've been waiting to use this. Let's get my big old starfish out here. So this one, now we have meters per second squared again. And what do we measure in that? We measure acceleration. And kilograms is going to be mass. Okay, so when force is constant, so now our graph is going to look a bit different because now we're looking at when force is constant. What's going to happen with acceleration and mass? So it's going to look kind of like a reverse J, right? Yeah, it's a reverse J. So higher acceleration equals less mass, usually. While, let's kind of draw like a little doop, 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 doop. Why higher mass equals less acceleration. Now, that's not always the case. If you think about a space shuttle and the rocket boosters that were attached to it, it would be harder for it to accelerate at a rapid rate. So just because something has a larger mass, it's going to require a lot more force to accelerate, but higher mass generally means less acceleration. Okay, or it's going to require more force, but in this case, force is constant. So if force is constant, a higher mass is not going to be able to accelerate at the same rate as a smaller mass. Okay. Ta-da! Okay, looking at this, I grab my little starfish. Okay, so the blank or blank, the greater the blank. And I have this, I gotta draw my little pyramid, I guess, there. So this is gonna be kind of a little relationship triangle. And we could have done these for speed and acceleration and everything else in the previous kind of little section, but I opted against it. Kind of hard to see, but that's okay. So I'm gonna have my F, my M, and my A. So if you're trying to solve for mass, you would divide force by acceleration. If you're trying to find acceleration, you would do force divided by mass. And if you're trying to find force, you're going to multiply. So this is just a relationship triangle. You might see these when you take a physics high school course. It's just kind of an easier way to remember the formulas if you can just remember the triangle, FMA, division. So to find acceleration, if you're trying to find this one over here, you're going to look at the formula across from it. If you're trying to find the formula for mass, you're going to look at the formula across from it. If you're trying to find the mass, or the formula for force, it's across from it. Okay, so that's how you kind of think of these things. And I never really understood the purpose of these when I was in high school, but I can kind of realize if you just memorize these and you remember which goes where, of course, I always overthought things. It's like, oh, bleepity bleep. I don't know where it goes. But so looking at that, my little rhino. What was it? James and the Giant Peach. That's what I was thinking. So the greater the mass or acceleration, so It's not an and, it's an or. The greater the force. Okay, so the greater the mass or acceleration. So it's not the and, it is an or, which is why I wrote or. Oh, I get to whip out. No, I'll save him for the next video. All right, Monsieur Lysiad. He's kind of doing a good job. Okay, so looking at this, did you know mass is a measure of inertia, the resistance of an object to acceleration. So if this is, a little versus, this is 2 kilograms versus 20 kilograms. The greater the mass, the greater the force required to increase its acceleration. Cover this one up. So the greater the mass, the greater force required to increase its acceleration. Therefore, acceleration is inversely, I'm sure I spell this right because I'm a terrible speller sometimes. There's that ELY stuff. Ugh. Inversely proportional to mass when the force is constant. All right, so they have an inverse relationship. They're kind of opposites. Okay, and the one part we did not do yet, let me kind of clear all this away, is this last part, the example question. Let me put my little raccoon back over here. Even though if you've made it this far in the video, who knows? So example question, what is the force needed to accelerate a 30 kilogram shopping cart at 3 meters per second? So if we know that force, that's what we're trying to solve for, it's going to be force equals mass times acceleration. Our mass is going to be 30 kilograms. So I was just joined by Maribel, Eric, and Kate from my Core 2. They're so excited. So they get to creepily stand there and watch me do this. So your mass is 30 kilograms. Your acceleration is 3 meters per second squared. So if you do force equals mass times acceleration, it's going to be 30 times 3. And don't forget your little units, in case I'm too lazy to write them. So 30 times 3, hopefully you don't need a calculator for this. 90, do not leave your number naked. Put 90 newtons. Ta-da!